So our question of the day, and you can answer this in Canvas, is why is it not practical to count atoms or molecules in dozens like we do donuts? So what is the mole? When we start looking at our macroscopic world, we see things like a dozen pencils, or 144 firecrackers, 13 donuts. We can express them as dozens of pencils, a gross of firecrackers, 13 would be a baker's dozen, 24 might be a case of soda. But when we talk about atoms, molecules, formula units, we can't count them out. They're too small to see. And we can't even really count out, 10 or even 1,000 of them because we can't see them. Even 1,000,000 we cannot see. So they're just too small. So what we're going to do is we're going to need a large number before we can even see them. And so what chemists do is we measure out atoms, molecules, and formula units using a really large number, so large that we can actually physically see what's happening. That large number is called a mole. That is 6.022 times 10 to the 23rd atoms, or molecules or formula units, depending on what we are looking at. So this number is known as Avogadro's number, but for shorthand, we also call it just 1 mole. So moles are not just tiny little furry creatures right now. They have meaning in chemistry. So since we're not going to be able to actually measure out this many of anything, counting them would take too long, we weigh out our items. So if we look at carbon, a mole of carbon is going to weigh 12 grams. Well, why? Let's think about this. Carbon, regular boring carbon, has 6 protons, 6 neutrons, and has an atomic mass unit weight of 12. A mole of carbon is going to weigh 12 grams. Now, what you might notice is 12 just keeps popping up. So, we'll say conveniently, that number stays the same. This works for all elements. The mass of 1 mole of any element is equal to the atomic mass in grams off the periodic table. So if we look at the periodic table, the mass that is given for every element of 1 atom in atomic mass units, or the mass of 1 mole of an atom in grams. So here, potassium 19, that is going to weigh 39.098 atomic mass units. That atom is invisible to the naked eye. If we take 1 mole of it, it's going to weigh 39.098 grams. We can see it. So the numbers on the periodic table are known as molar masses. They are the mass of 1 mole of any substance. For example, 1 mole of sodium atoms, 22.990 grams. 1 mole of 10 atoms, that's going to be 118.710 grams. What about sulfur? What is 1 mole of sulfur atoms? 32.066 grams. What is the point and why do we care? What use is this to us? Because 1 mole of these substances contains 6.022 times 10 to the 23rd atoms. They may weigh different amounts, but they have the same number of atoms. When we are looking at chemical reactions, we have to know the number of atoms involved. That's what we've been doing with our chemical reaction formulas this whole time. So I've got pictures here, what 1 mole of those substances looks like. They all have the same number of atoms. So what if we want to know the molar mass of a compound? Well, it's not as complicated as it sounds. Let's start by looking at water. 1 water molecule has 2 hydrogen atoms and 1 oxygen atom. An oxygen atom has an atomic weight of 16 AMU. The hydrogen atom, 1 AMU. So that means a single water molecule is going to weigh 18 AMU. We have 1 oxygen and 2 hydrogen. What about 1 mole? So 6.022 times 10 to the 23rd molecules of water. Well, that's going to be the exact same number, just in grams. So 1 mole of water is going to be 18 grams of water. So you're probably saying, I really wish there was an easy to use tool to do these conversions. And there kind of is. We have the mole map. Now this is a handout. It's also linked in Canvas. This mole map will allow you to go back and forth between how many moles, what's our volume, what's our number of particles, number of grams, liters of gas. So this is going to be our useful tool. This is a convenient tool that is going to help us convert between various quantities when we're dealing with large-scale chemistry. So if we had 2.75 moles of phosphorus atoms, we look at the mole map, we should be able to go from moles to number of grams. It tells us to multiply by the molar mass. So the molar mass is the mole of an element from the periodic table. So phosphorus atom weighs 30.974 AMU. So 1 mole of phosphorus atoms is going to weigh 30.974 grams. So if we had 2.75 moles of phosphorus atoms, and we know how much 1 mole weighs, we can do the conversion and get that that is 85.2 grams. What if we wanted to know how many moles we have? If we had 8.02 times 10 to the 24th atoms of neon. So remember, mole is a counting quantity. Doesn't matter if we're looking at donuts, eggs, or tires. A mole is just a counting quantity. So 1 mole of anything in chemistry is going to have 6.022 times 10 to the 23rd atoms. If we use our mole map, we are going to do conversions. So here we have atoms. We are going to convert from atoms to moles. So we are going to divide by 6.022 times 10 to the 23rd atoms. So here we have how many atoms of neon? We're going to take 1 mole of neon is 6.02 times 10 to the 23rd atoms of neon. We're going to cross those out, and we're going to get that 6.02 times 10 to the 24th atoms of neon is 13.3 moles of neon. So the mole map also allows us to do some conversions. specifically some gas conversions. So atoms are very small. Gas particles spread apart. Because of this, there is a natural phenomenon that at standard temperature and pressure, also called STP, which is 0 degrees Celsius, 1 atmosphere of pressure, with those situations in place, 1 mole of any gas, does not matter what it is, will occupy 22.4 liters. They will not weigh the same, but they will have the exact same volume. So they're all going to be 22.4 liters. Now, what you may also notice is that even though the atoms weigh more, so argon weighs way more than helium, the atoms themselves are so tiny, they are not appreciably affecting the volume of the container itself. They are tiny. So gas occupies 22.4 liters at standard temperature and pressure. So, okay, let's say we had 175.5 liters of argon. How many moles would we have? So, no matter what, it doesn't matter what the gas is. They're all the same volume at standard temperature pressure, STP. So we are going to use the mole map. We start with the 175.5 liters of argon. 1 mole of argon occupies 22.4 liters. That is going to give us 7.835 moles of neon. So that little last part, that bottom right corner, that deals with molarity and liters of substances. And we are going to get into that, just not yet. Okay, it's coming. Preview. So, couple of things. Do not forget to take into account diatomics. So, oxygen, the atoms are not separate. They travel in pairs. So 1 mole of oxygen molecules is going to weigh 32 grams, not 16. And so 6.02 times 10 to the 23rd molecules of oxygen, not atoms of oxygen. So be careful for the ones that travel in pairs. They like to come visit and have fun.